Assalamualaikum. My name is Zunaira Sajid and I'm from batch 2. The topic of my presentation is the membrane used in industrial wastewater treatment. Content of my presentation is abstract, introduction, membrane technology for wastewater treatment, classification of membrane technology, applications in industries, advantages of membrane technology, last but not the least, conclusion. First of all, I'll tell you about the abstract. As we know that conventional wastewater treatment methods have progressed in treating effluents for discharge throughout time, making treated wastewater reusable for industrial, agricultural, and home users requires advancement in wastewater treatment technologies. Membrane technology has proven to be the most effective method for treating wastewater from various effluent sources. Membrane technology is one of the most recent innovations found to reduce contaminants to desirable levels effectively. Membrane bioreactors for biological wastewater treatment offer several benefits over traditional treatment despite some drawbacks. The principle of the membrane technology, the classification of the membrane technology processes according to pressure, concentration, electrical and thermally driven processes. Its application is various industries and its benefits are all covered in this paper. Membrane technology is widely used in the wastewater treatment process. Introduction. The fast industrialization, urbanization, and population boom of the previous few decades have contributed to a massive rise in water demand. The lack of fresh water have prompted the creation of innovative therapeutic methods. Many companies release their waste products straight into the environment, which has given an impact on aquatic ecosystem and biodiversity. A difficulty in protecting the environment is the daily release of hazardous waste pollutants. Every day, tons of liquid and solid garbage are produced worldwide. Managing the disposal of contaminants is a severe challenge due to constantly expanding population and dwindling landfills. Although many technological advances have already been achieved to test the limits, much work remains. The effects have been felt for a long time in the air, land, and water. The chemical oxygen demand and biochemical oxygen demand, suspended and dissolved particles, chromium, surfactants, and other toxicities of the water bodies, where they discharge and are significantly impacted by the hazardous effluents produced in large quantities. Consequently, these effluents should be handled appropriately to prevent environmental harm, the toxicity of aquatic life, and human ingestion. When the first water desalination plants based on RO technology was created in the 1960s, the development of membranes began. This was one of the Environmental Protection Agency has acknowledged it as the best available technology due to its wide range of uses in numerous industries. Low energy consumption, constant separation, and simple scaling up are the advantages of membrane processes. This was one of the extensively used and affordable technologies for the wastewater treatment. Membrane technology for wastewater treatment. A membrane in its simplest form is a barrier that divides two phases by limiting the movement of specific components across it. Basically, the invention of membranes dates back to in 18th century. Since then, numerous advancements have been made to membranes to better suit a variety of applications. Chemical species are separated through membrane interface using membrane separation techniques due to differences in transport rates. This transport rate is influenced by the component's concentration, its mobility, and driving force within the interface. Chemical affinity, membranes, morphology, and solute molecular size are the significant determinants of effective chemical component separation. The types and modules of membrane affect how well it separates. Now I'll tell you about the types of membranes. So typically there are four membranes: composite membranes, organic and inorganic, porous and non-porous. Membranes can be isotropic or anisotropic based on their characteristic properties. Uniform composition and physical structure characterize isotropic membranes. When they are non-porous, their use is severely constrained by the low permeation fluxes. However, when they are porous, their permeation fluxes are rather considerable. In many microfiltration membranes, isotropic microporous membranes are used. On the other hand, isotropic membranes are composed of many layers with various structures and composition and are not uniform throughout the membrane region. A more significant, highly permeable layer in these membranes supports a thin layer film. Reverse osmosis techniques are where the most frequently uses. Here are the sketch of the types of different membranes. So as I discussed before, membranes are categorized as organic or inorganic based on the composition of their constituent material. So synthetic organic polymers are used to create organic membranes. Membranes for pressure-driven separation techniques including reverse osmosis, microfiltration, ultrafiltration, and nanofiltration are often composed of synthetic organic polymers. These materials include, among others, cellulose acetate, polyethylene, polytetrafluoroethylene, and polypropylene. Ceramics, metals, zeolites, and silica are some examples of materials used to create inorganic membranes. They are widely utilized in industrial applications such as hydrogen separation, ultrafiltration, and microfiltration because they are chemically and thermally stable. The basis of membrane technology is the selective permitting of some constituent to pass through the membrane while restricting the passage of others. Typically, this process needs an outside driving force to make it happen. The membrane process is categorized to make them easier to grasp based on the type of driving force used to separate the components in the wastewater. Many different driving forces cause solute partition such as pressure differences, which includes micro, ultra, nanofiltration, and reverse osmosis, and concentration differences across membranes, which includes dialysis and potential field applications of ion exchange membranes that cause ion migration throughout the membrane, and it includes electrodialysis, electrochemical separation. First of all, pressure driven membrane separation process. The most widely utilized technology for wastewater treatment is pressure-driven membrane processes using pressure to separate and permeate the retention phases. This method is utilized to reconcentrate the dilute solution. The permeate phase contains fewer solutes and the retention and feed solution. The applied pressure determines the total operational cost of the system. When it comes to pressure-driven membrane processes, RO is renowned for its high effectiveness in the separating monovalent ions like sodium ions and chloride ions up to 99.95%, as well as tiny particles like microorganisms. Microfiltration. A porous membrane is used in the physical separation method known as MF. Based on the membrane's pore size, it eliminated dissolved solids, turbidity, and microorganisms using a sieving mechanism. Particles larger than the membrane pores, 0.1 to 0.2 meter, can be removed, while those more minor can only be removed in part. To lessen the fouling, it serves as a pre-treatment for UF and post-treatment for granular media filtration. Membrane components in MF might be either organic or inorganic. Polyvinylidene chloride and polyamide, polysulfone, cellulose acetate, and other polymers make organic membranes. While porous alumina and metals make inorganic membranes, it is appropriate for isolating suspensions and emulsions and can hold up to 40% of the organic material, while water, monovalent ions like sodium, chloride ions, dissolved organic materials, tiny colloids, and viruses might pass through the filter. These filters primarily remove silt, algae, protozoa, and bacteria. Next one is ultrafiltration. The widely used low-energy UF membranes accomplish the removal of harmful microorganisms, macromolecules, and suspended materials. These membranes have pores with diameters as large as 0.1 mm. Its shortcomings include the inability to remove some dissolved inorganic impurities from water entirely and the need for frequent cleaning to maintain a proper water pressure stream. Pressure or concentration gradient must pass across membranes to separate the particles. These membranes hold onto silica, endotoxin, proteins, and viruses. The pharmaceutical, dairy, beverages, food processing, and other sectors use this technology as a part of pre-filtration process in RO. UF is also employed to preserve the membrane. Next one is nanofiltration. The NF membrane for nanofiltration was initially developed in the late 1980s. Its characteristics are in between those of an RO membrane and a UF membrane. This procedure moves a molecular mixture to a membrane surface by applying hydrostatic pressure. While specific low molecular weight solutes and the solvent pass through the membrane, other elements are trapped. Lower operating pressures are necessary because it is adequate to eliminate ions that significantly increase osmotic pressure. NF cannot remove soluble components as proper pretreatment is required for the highly contaminated waters. The membranes are impacted by free chlorine in the feedwater. Applications for the NF membrane include wastewater treatment and desalination, dairy and medicines. Membranes used for NF are made of polyamide composites, cellulose, acetate blends, or modified UF membranes such as sulfonated polysulfones. Next is reverse osmosis. Only water molecules can pass through the pressure-driven or a process which is utilized to remove dissolved chemicals and tiny particles. Water must be able to pass the osmotic pressure if enough pressure is provided to the RO system. Higher penetrability, more excellent selectivity, and higher fouling resistance all generally increase the efficiency of the RO membrane. One of the best membrane separation technique is the water is pushed through a membrane under pressure to remove the minerals and nitrate. Due to the size of the pores, RO retains almost all molecules except for water, and the necessary osmotic pressure is substantially higher than that of MF. In comparison to other membrane technologies, RO membranes are more expensive and frequently subject to fouling. In some circumstances, a necessary pretreatment is necessary. Forward osmosis. Water is moved through a semi-permeable membrane using the FO mechanism, which depends upon the osmotic pressure gradient to move water from a feed solution to a drying solution. The FO mechanism's clear advantage over conventional pressure-driven membrane technology is that it does not require high hydraulic pressure. As a result, it motivates to reduce energy consumption and maintenance expensive for membranes. A FO membrane's effectiveness in desalinating water was engineered and tested. The commercially available FO membrane are polymerized using PODH and polytriazole co-oxadiazole cohydrazine is used to filter reactive acidities from wastewater produced by the textile dye industries. Concentration-driven separation process. The concentration-driven osmotic process includes the concentration gradient at isobaric and isothermal conditions control the function of the biological membrane system. Artificial kidneys are the most prevalent example of synthetic membranes made using a concentration-driven membrane method. This group includes FO and dialysis since the concentration gradient becomes necessary for membrane separation in these procedures. Perevaporation. By applying vapor pressures via porous or a non-porous membrane, perevaporation removes tiny amount of volatile components in liquid mixture. This technique combines membrane permeation and evaporation to separate the liquid mixture according to each component's preference. It is used to separate volatile organic molecules and hydrocarbons. Basically, it is used in petrochemical industry. The motivating element behind this strategy is concentration difference. Its foundation is a solution diffusion mechanism which causes the vapor to develop as it permeates. As a later step of the process, the vapor produced during the process is eliminated either by providing low pressure or by flowing an inert substance. The separation of the ethanol-water combination is an illustration of this technique. Next one is gas separation. The process of gas separation is likewise based on the exact mechanism of evaporation. Initial feed absorption into the membrane is followed by the permeate diffusion through the membrane and lastly permeate desorption at the low pressure site. Selectivity is a crucial component of the GS process. The solution diffusion method is used to move gaseous molecules through the membrane. This method can separate polar vapors and gaseous mixtures utilizing asymmetric, homogeneous, or polymeric membranes. In GS, a hollow fiber polymeric membrane structure is typically used. However, the membrane material's primary issue emerges when it is used in high pressure applications such as petrochemical and petroleum refineries, natural gas treatment, heavy hydrocarbon separation, and so on. Electrical driven membrane separation process are used to apply electric potential during electrodialysis, which removes specific ionic compounds from an aqueous solution. IEMs are created using less polymeric materials with set ionic charge groups in the polymeric matrix. Cation exchange membranes and anion exchange membranes are the categories into which IEMs fall. Whereas AMs have positively charged groups, CMs have negatively charged groups in their polymeric matrix. It is primarily employed in the pharmaceutical, food acid removal, and saltwater desalination industries. Ion exchange membrane process. It includes ionic groups which are connected to polymeric backbones in the IEMs, semi-permeable membranes. Magnetic ion exchange and fluidized ion exchange are combined in the procedure. Many applications have benefited from the concentration and ionic groups. An effective non-porous anion exchanger removes little organic matter. Ion functionality and polymer structure can be used to categorize IEMs. The electrochemical interactions of the molecule is the main driving force of IEMs. The last one is temperature-driven membrane separation process, and it includes membrane distillation. Ionic groups are connected to polymeric backbones in the IEMs, which are semi-permeable membranes. Magnetic ion exchange and fluidized ion exchange are combined in this process. Many applications have benefited from the concentration in ionic groups. An effective non-porous anion exchanger removes little organic matter. Ion functionality and polymer structure can be used to categorize. Liquid membrane. Between two aqueous phases with various compositions, a thin layer of the organic serves as a semi-permeable membrane.